Okay, so hi everyone again. Colleen, my name is Colleen Bertoni. I gave the OpenMP intro talk before. This is going to be about math libraries on Polaris. So I'm not going to really get into details about like how to use specific math library function in the code itself, but this is more about where to find the libraries on Polaris, how to link them in, and debugging tips. So just a quick outline. I'm going to do kind of a little getting started. Brian covered a lot of this earlier with the modules and compiler wrappers, but I'm going to do a quick review just because when we're linking in math libraries, it's very important to understand other things that are being linked in and what's happening during the compilation and linking process. Then I'll have some slides talking about available math libraries. Matt pointed out the CUDA ones earlier, so you'll see that again. Then some tips on sanity checking that I've found useful in my own work on Polaris. And finally, just a couple of debugging examples / game where I have a couple of common problems people can run into when they try to link in libraries, and then the solution to them. So with that, let's get started. So just environment modules again. So yeah, these are handled by modules on Polaris. Shown here, you can see what you have with the module list. The default is shown in bold, Bertoni and the HPC. The modules, it's important because they basically set your path, include path, LB library path, etc. So the modules you have loaded impact what is linked in and what programs you can see. So we just recommend always checking what your module list is, both when you compile and run. So the compilers, just ones that you'll be familiar with, like other things with GCC, NV, C++, NV Fortran, etc. The compiler wrappers, Brian talked about this, it's capital C, lowercase c, FTN. These select specific underlying wrappers like GCC or NVH or NVC based on the modules you have loaded, or usually it's the program and you have loaded. So I can refer to almost any underlying compiler on the system. The important thing from math libraries I wanted to point out is possibly on other systems, BLOS or some other math libraries might be linked in by default, but that's not the case here. But you can always check. So yeah, Brian mentioned this slide earlier, the cray print ops equals lib. This will tell you which libraries are linked in as like kind of hidden part of the compiler wrapper. So what we see here is it's linking in a lot of MPI libraries. We don't see any BLOS. So the important thing is compiler wrappers hide, or they will pull in a bunch of MPI for you, but not math libraries. You'll either have to link it in explicitly, or sometimes just loading a module will link things in for you. So with that, let's talk about some available math libraries. Actually, first, I just wanted to be clear. So like with the compilers, libraries are managed by modules on Polaris. So again, the modules will set your LE library path or your library. The libraries are dynamically linked in by default. Just to be really, really clear about this, that means that the library routines, they're checked at compile time, but they're not linked into your executable at compile time. If we were doing static linking by default, it would pull the entire library in, or parts that you needed, and at actual compile time. But since it's dynamic linking, they're actually pulled in, they're loaded at runtime. So you do need to be careful of the environment at runtime as well as compile time. Still at compile time, you will need to have the libraries in your path because the linker will usually check the symbols that are linked into the program that exist but they won't actually insert it into the executable again on static libraries. With all that said, there are of course exceptions. But for instance, the NVIDIA provided libraries are usually linked in with -rpath by default, which means it hard codes the path, the library. So what you have so it doesn't matter if you have a different module loaded at runtime versus compile time, it will use the one you used at compile time. So generally you can use -v to confirm which libraries are being pulled in, and I'll have other examples of how to just double check what libraries you think you are linked to are the ones you're actually linked to. I'll have that a little bit later. So like the compilers, libraries also manage their modules. Generally, you'll do module load library name to set the environment so the library is pulled in. So for example, one of the libraries to talk about in a second is craze libsci. So you would do module load cray libsci. And just if you want to see what this is doing, you can always do module show cray libsci. This is nice because it just tells you exactly what the module is doing. So the environment variables it's setting or anything like that. And also this is to show you modules aren't black magic. They're literally just a small file that sets variables to other variables or to strings. And if you want, you can always write these yourself as well. Just not black magic, it's just setting standard Linux environment variables. So for environment variables, or for MATLAB, sorry. So module avail will basically tell you everything that's available in the system. I'll start by pointing out the GPU math libraries. Some of this, the way you do this will be different depending on the program environment you have loaded. And then there are also some GPU libraries that are not part of the standard Cray or HPE environment, and I'll have a slide for those later. But this is starting with the CUDA ones. So these are available in the NVHPC modules. The default when you log on the system is 21.9, but I think we have up to 23.3. So if you want the newer ones, feel free to just module switch the NVHPC modules to the newer one. Like Matt mentioned, a bunch of math libraries, cuBLAS, cuSPR, cuRAN, cuSPARSE, cuFFT, cuFTW. These are, if you look at the code to the right of the screen, you can go and look at all these. NVIDIA Path, MathLibs, lib64, so you can see all the ones that are available. If you have pure CUDA code, you can link this in with C, CUDA, -L cuBLAS, this is for cuBLAS, and then the path to lib cuBLAS. You can also do this with, of course, with Fortran, with CUDA lib equals cuBLAS 2. And NVIDIA documentation is really good. There's a link here. That was with the program environment NVHPC. So this is if you want to use the CUDA math libraries, but from program environment GNU. So these are either in the CUDA toolkit standalone modules or the NVHPC modules, but you might need to hard code the path in the libraries. So the right side again shows just listing the directory for the standalone CUDA toolkit. So you can see it, yeah, basically all the same stuff. Here the compile is a little different because if you're using the GNU compiler, you need to link in a couple of different libraries, but basically the same. -L cuBLAS, just -I to give the header files, -L to give the path to the math libraries. And this link is just the same because in both cases, the NVIDIA math libraries. On the CPU side, we have NVIDIA libraries, so there's a BLOSUM and LAPACK. They can be found under, again, NVIDIA Path library, or the NVIDIA path compilers lib path. There's ScalePack if you want to. It's under that directory too, but COM libraries. And just like before, you'll need to give the path with --L path and -l LA path or blast, whatever you need. And again, NVIDIA has nice documentation on it. Some more CPU libraries. So there's cray-libsci. I mentioned this before, and this is actually what I tend to use on Polaris with the code that I work with. It says BLAS, LAPack, ScalePack. You can get it with module cray-libsci. This will also actually set the library paths for you, so you don't have to explicitly give --L path. But that's only if you're using the cray compiler wrappers, not the case if you're using MPI compiler wrappers, like with LVM or one MPI module class. And then you can link in, you should check which library you want to link in, whether the serial multi-threaded or serial multi-threaded MPI is denoting that it's using ScalePack. There's also Cray's FFTW as well. Cray has really nice documentation or man pages. You just type man intro libsci or man intro FFTW for more information. Then there are a couple of other non-Cray supported ones that you can find under module use, soft module files, GSL, Magma, Ginkgo. AMD also has CPU libraries. This might be worth a try because CPUs are AMD CPUs. There's also, like Brian mentioned, you can run one MKL, so Intel MKL, on NVIDIA GPUs. You can do this with module one API. So it takes Intel SQL APIs and translates them into CUDA calls. More information is this link is. So just a couple of tips for sanity checking. So again, dynamic linking defaults. One thing that's useful is if you want to see what libraries your executable is linked to with whatever your environment is set to, you can run LDD and executable name. So here I'm doing LDD games00.x. This is a quantum chemistry code I work with a lot. And here we can see which libraries it's all linked to. So I'm using Cray's libsci. Another thing that you can do if you're interested in a specific function name is you can ask the linker, where is this exact definition being found? So here, if I'm interested in dgem, I can say, so this code is Fortran code, so ftn -wl -y dgem, and the underscore is because Fortran. And it will tell me, okay, the definition of dgem that you're pulling from is from Cray's libsci here. And for instance, if I had switched instead of using Cray's libsci to using NVIDIA's BLAS LAPack, I now see it says, okay, this is coming from NVIDIA HPC SDK, lib LAPack. So just in case you're like, I don't know where these dgems are coming from, this is useful to if you ever find yourself in a situation where you need to know. The last thing for sanity checking is a lot of people at ALCF have a lot of support or have a lot of experience debugging as well as running on Polaris. So please reach out if there are any issues. Of course, you can talk to the people in the room too. I wish I was there to help, but you can also email this email address. And then the last thing is just a quick debugging example / game. I'll just go through 3 different scenarios, and I will give you a few seconds in between each one to think through it yourself, and then go through the solution. So debugging game number 1. I know I've encountered this many times, maybe other people have, but so these are all going to be examples from compiling this code that I use a lot. So I try to compile it. but I get at compile time an error saying undefined reference to d-dot, dcopy, dscale. So these are all loss functions. So if I get undefined references, that's a problem. So I'll give you guys like 5 to 10 seconds to think about how you would handle this situation. Okay, so the issue, so usually this means that there's a library missing at link time. So either missing the path with the -L, or sometimes a module which sets the library path isn't loaded, or maybe there's a flag like CUDA-lib kubos is missing. So in this particular instance, I was using module load crelib which sets the path to the BLAS library. So all I had to do was reload module load crelib and then okay, next example. So this time, make sure all my modules are loaded. Everything looks good, and then I'm trying to compile this CUDA code. capc f.c -CUDA -L kublos. But at compile time, so I get another compile time error. Can't find -L kublos. No such file or directory. So again, yeah, something I've encountered before. So I'll give another 5-10 seconds for people to think through this. Okay, so here the issue was the path to the library wasn't set. So the linker couldn't find the definition. So it says I can't find it. So the solution is just to add -L NVIDIA mathlibs /lib64. Again, different modules might add that for you, but in this particular instance, it doesn't. So that path isn't in the list of search libraries by default. This solves the problem. There are other ways of solving it, but in this case, this is what I did. And then the last problem, so this time everything compiled fine. And then I grab it and try to run JavaScript, so mcat-exec, and running 8 ranks per node, binding to the CPUs, the depth of 8 in between them. But then I get this error while loading shared libraries, the fabric cannot open shared object file, no such file or directory. So yeah, again, somewhat common problem. Wait 5 to 10 seconds so you guys can think through it. Okay, in this case, I didn't have the module set correctly at runtime. This isn't directly a math library one, although I've encountered it with other math libraries. So at this point, I had the module set correctly at compile time, so compiled fine. But then at runtime, I didn't have my module set correctly. So I get a runtime error saying I can't find this library you promised me would be. And you can always check this again with LDD. And then you would see it says, oh, I need this, I depend on this library, but it is not. So the solution is just to load the needed module. Okay, so just in summary, just keep in mind Polaris uses compiler wrappers. So things are linked in by default, but with not that you have to link them in yourself. You can use module avail to see additional available modules. There are a lot of them. Definitely encourage people to do sanity check just to see if what you think you're linking in is what you're actually linking in. And of course, please reach out to ALCF support if there are any issues. I wish I was there to help in person. But if not, you can email this or to other people who are currently with you in person. With that, that's all I have. Thanks.